Hello. Our common theme of studying various parts of algebra has been studying zeros of polynomials. So far, we have been working with single variable polynomials and studying them from different angles. And that was our source of motivation to define ideals, to define prime ideals, maximal ideals, even understand irreducible polynomials, factorization, unique factorization domains. We used that as a motivation and studied principal ideal domains and so on. Now, we want to shift from single variable polynomials to multivariable polynomials. We want to understand zeros of multivariable polynomials. The easiest such polynomials would be linear polynomials. So we want to understand equations that are given by degree 1 polynomials. So for instance, we can look at this system of equations, a sub 1 1 times x1 plus a sub 1 2 times x2 and so on equals to b sub 1. Similarly, for the other variables, the same variables but different equations, we can set up a system of linear equations. Of course, you have studied these type of equations when a sub ij's are either complex numbers or real numbers in linear algebra. Earlier in 100b and in this 100c, we've seen how useful it is to think about linear algebra and vector spaces not only over complex numbers, but also over other fields. Now, we want to answer the same type of questions not only over fields, but over other rings. One thing that I have to point out is that in the case that the a sub ij's are complex numbers or real numbers, our main algorithmic tool has been the so-called Gauss-Jordan elimination process. So if you remember, this process involved eliminating one variable at a time. Or if I drop the variables and work only with coefficients, this was a process involved with reduced row or reduced column operators that can help us to essentially eliminate variables and deal with one variable at a time. And if you think about it, this reduced row or reduced column process involves only addition, subtraction, multiplication, or division, which means that we should be able to do the same process over an arbitrary field. And one can do that. We are not going to discuss it here again, but it's not surprising that one can do this, and it is indeed the case. But the question is, how much of the same argument can be done over an arbitrary ring? Notice that even if I give you only one variable and one equation, then it's not as easy as the case of fields. So if I give you the equation ax equals to b for some a and b in a unital commutative ring A, then this equation does not necessarily have a zero in A. Indeed, it has a zero in A precisely when B is a multiple of A. Now, if A has a zero divisor, then this equation might have multiple zeros. So in general, for an arbitrary ring A, even an equation of the form ax equals to b is not that easy to be handled. But nevertheless, we have an understanding of how we can approach it. We ask ourselves whether or not b is a multiple of a. If we can answer this question, then if a does not have zero divisors, this equation has a unique solution, and so on. So what is clear is that the ideal structure of A plays an important role to answer this question. So after fields, which have the easiest ideal structure, they have only two ideals, either 0 or the entire field. So after fields, the next ring that has easiest type of ideal structure, they are either PIDs or even easier than that, Euclidean domains. So we can ask ourselves whether or not we can solve a linear equation over a PID, over a Euclidean domain, and so on. So that would be our next goal. Over a field, when we were discussing linear algebra, we've seen the importance of vector spaces, how to define vector spaces, how to think about, instead of thinking about the inhomogeneous solution of Ax equals to B, we can think about the solution of Ax equals to 0, which means the kernel of this linear algebra math, this linear transformation play an important role. Of course, image means that does B belong to the image of Ax, so that one also plays an important role. So what I'm saying is that in linear algebra, meaning equations, linear equations with coefficients over a field, this concept of vector space, linear transformation, image of a linear transformation, kernel of a linear transformation can help us a lot in order to understand equations of the form Ax equals to B. That's why we want to develop a similar concept for an arbitrary unital commutative ring R. So what do we have in a vector space? In a vector space, we have a set of scalars. In that case, it was a field. And we have an abelian group, V. And there is a scalar multiplication between the set of scalars, the field F, and the set of abelian group that we have. And this scalar multiplication had certain properties. 1 times every vector was the vector. The multiplication inside the field is compatible with this scalar multiplication. We have distribution law both on the ring side and on the vector space side. So these were the axioms or conditions of getting a vector space. What we are going to do is to impose the same conditions, but this time we assume that set of scalars are just rings. And what we end up getting, we are going to call that's an R module. So let's go slower. Suppose R is a unital commutative ring and M is an abelian group. We say M is an R module if we have a scalar multiplication with the set of scalars R over the abelian group M. We often denote this scalar multiplication simply by Rm with no dots, but for today's lecture, I'm going to emphasize on the dot. So given an element R of the ring capital R and an element M, small m, of the module capital M of this abelian group capital M, we can talk about R times M. And this multiplication has the following properties. 1 times M, this is the unity or identity of the ring capital R, times M, no matter what M is, ends up giving us M. R1 times R2 times M is the same as multiplying inside the ring and then multiplying and then using scalar multiplication. So these multiplications are compatible. Multiplication inside the ring and the scalar multiplication in the module are compatible with each other. And we have distribution both on the ring side and on the module side. So these are the assumptions. These are the conditions in order to get an R module. let's review some examples, important examples. Of course, as I have motivated it, if F is a field, then V is an F module if and only if it's an F vector space. So an F module, V is an F module exactly when it is an F vector space. So over a field, the concept of vector space is equivalent to the concept of modules. Now, for an arbitrary ring, do I have an interesting module? So if you remember, for vector spaces, we showed that at least the ones that can be spanned by finitely many vectors, we found out that there is a basis, and from there we deduced that every finite dimensional vector space, we define dimension as well, every finite dimensional vector space is isomorphic to n copies of the field F, where we are using the common additive structure of this Cartesian product, and the scalar multiplication is done component-wise. We can do the same for rings. We don't have the same result, but at least we can consider the r to the n times Cartesian product of r by itself n times. So r to the n for an arbitrary ring R is an R module. And what is the scalar multiplication? Similar to the vector space case, it's component-wise multiplication. So R times a vector is R times the first component, R times the second component, and so on. Okay, that's an important example. Another example, which plays an important role later as well, if I give you a ring R, I can consider multiplication of R on itself. Then I ask myself, do I have a subset that is invariant under this multiplication? And it's an abelian subgroup. So what are those? Let's write down the conditions that I'm saying. So we are asking if I is a subset of R, and for every A inside I and R inside R times A is inside I, and I is an abelian subgroup, then of course with multiplication that comes from the ring R, I would be a module, because it has a scalar multiplication that comes from multiplication in the ring, and it has additive structure. But if you remember, these are precisely the conditions of being an ideal. So what I'm saying is that a subset of R is an R module with respect to multiplication of the ring R in the ring R, precisely when it's an ideal. So there is a bijection between submodules. So the subsets of R that are modules with respect to the multiplication of R and the ideals of R. So here I wrote it only in one side. If I is an ideal of the ring R, then I is an R module with respect to the scalar multiplication that's given by the multiplication inside the ring R. Okay, so far we have three examples: vector spaces over fields, R to the n for an arbitrary ring R, every ideal of R. Another important example, maybe we do not discuss it as much now, but we did it earlier for fields. If R is a subring of R prime and shares the same identity, then we can view the larger one as an R module. So R prime would be an R module. If you remember, we have done this point of view for fields. So whenever we have a field extension E over F, we can view E as an F vector space. So this is exactly the same point of view here. So sometimes we say that R is an extension, R prime is an extension of R. So R prime contains R as a subring, and they share the same identity. From there we can deduce that R prime is an R module. Okay, so with respect to the same multiplication that comes from the ring, the larger ring. The last example that I'm going to mention plays an important role in this course as well. What is it? Every abelian group is a Z module. And of course, vice versa, because every R module is a abelian group. In particular, every Z module is an abelian group. But we are saying that the converse is also correct. They are essentially the same thing. So if A is an abelian group, I can define a scalar multiplication on the set A from the ring Z. So A is a Z module. So what is the scalar multiplication? So I have to tell you what is n times A, where n is an integer and A is an element of this abelian group, capital A. We have already defined it long ago. So n times A is nothing but A plus A plus A, n times, if n is positive. If n is 0, we just set it to be 0. And if n is negative, we take negative of A inside this abelian group and add it negative n times. Remember, n is negative, so negative n is positive, and so on. We have seen this long ago, and we've seen many properties of this. If you remember, we have shown that n plus m for every integer n and m times a for every a inside this abelian group is the same as na plus ma, and n times a plus b is the same as n times a plus n times b, essentially because addition is abelian, is commutative. So these conditions, together with the fact that 1 times a is a, immediately implies that a is a Z module. As always, when we see a new object in mathematics, we have to ask ourselves, what can I say about the substructures and homomorphisms for this object? So for modules, we do the same. So we ask ourselves, what are the submodules? I have already mentioned the word submodule, but let's define it properly. And what are the homomorphisms of our modules? Let's start with submodules. Suppose M is an R module. A submodule, of course, is a subset. A module has two structures, if you remember. One of them is the abelian group structure. The other one is coming from the scalar multiplication. So N should be a module with respect to the addition that comes from M and the scalar multiplication that comes from M. I can write it like this, that N should be an additive subgroup of M that guarantees the additive structure is compatible with M, and it should be closed under scalar multiplication. So that way I can define scalar multiplication, restrict it to N, and get a scalar multiplication there. And the other properties of modules are already there, because we already have the distribution on both sides, as M is an R module. And we do already have that 1 times every element inside M is M, and therefore the same is true for this submodule, and so on. So this automatically shows that such a subset is an R module with respect to the same scalar multiplication and addition as M. Okay, so now how about module homomorphisms? So suppose M and M prime, both of them are R modules. What is an R module homomorphism? It's going to be a function from the first object to the other one, such that it preserves the structure. So here we have addition and we have a scalar multiplication. So F should preserve addition, and F should preserve the scalar multiplication. We can also write it the same as linear transformations and say that F should preserve linear combinations of elements inside M. So I can alternatively write only this, that F of m1 plus r m2 is supposed to be f of m1 plus r times f of m2. If this equality is true for every r and every mi, for every r inside the ring and every mi inside the module, then we can get both of these results out of it. Okay, so that's the definition of R module homomorphism. Now, similar to linear transformations, we are going to show that image and kernel of module homomorphisms are submodules themselves. Notice that I can define image and kernel as f is an abelian group homomorphism. So clearly, image of f and kernel of f are subgroups of the codomain and domain respectively. So again, the thing that I want to show is that if I give you an R module homomorphism, then its kernel and its image, both of them, are submodules. Of course, image would be submodule of the codomain, and kernel is submodule of the domain. So let me repeat that because f is a group homomorphism, we automatically know that image of f and kernel of f, we have already proved that image of f and kernel of f, both of them are subgroups. So next, I'm going to show that they are in fact closed under scalar multiplication, and therefore they are submodules. So let's start with image of f, and let's pick some element inside the image and pick some scalar inside the ring, and we want to show that r times this element is still inside the image. So let's say y is an element inside the image, and r is an element inside the ring, and we want to show that r times y is still inside the image. But what does it mean that y is inside the image? Y is inside the image means y is f of something in the domain. So y is f of m for some m inside the domain. Now, we are interested in r times y. That means I'm interested in r times f of m. But what is f? F is an R module homomorphism, which means f preserves a scalar multiplication. That means r times f of m is f of r times m. That means it belongs to the image of f. So altogether, we deduce that image of f is closed under scalar multiplication. Now, we want to show that kernel of f is also closed under scalar multiplication. We have already proved the image. Let's see why kernel is closed under scalar multiplication, and therefore it's a submodule. We have already discussed that this is an abelian group, so it's enough to show that kernel of f is also closed under scalar multiplication, from which we can deduce kernel of f is a submodule. So again, we are going to pick some element inside the kernel and some scalar r, and we want to show that r times m is still inside the kernel, which means I need to show that f of r times m is still 0. What do I know about m? M is inside the kernel, which means f of m is 0. We are interested in showing that r times m is in the kernel, which means I need to show f of r times m is 0. What is f? F is an R module homomorphism, so it preserves the scalar multiplication. That means f of r times m is r times f of m. Now, f of m is 0 because m is in the kernel, so we get r times 0. Now, r times 0 is 0. Why is that the case? What do we know about the scalar multiplication? How can I know that r times 0 is 0? Here is a quick reminder that we have had a similar result for vector spaces, and let's see why this statement is correct. R times 0 is clearly r times 0 plus 0, because 0 plus 0 is the same as 0. Now, scalar multiplication, it has distribution property on both sides, in particular on the module side. So it is r times 0 plus r times 0. Now, the module and addition is a group. So I can cancel out this r times 0 by this r times 0, and end up getting that this one of them is just 0. So r times 0 is 0. Notice that similarly I can show 0 times anything is 0. So 0 times m is 0 plus 0 inside the ring this time, times m. Again, we use distribution this time on the ring side, and we get that 0 times m plus 0 times m is 0 times m, and similar to the above argument, the fact that an addition is a group allows us to do the cancellation, and we end up getting that 0 times m is also 0. So this part is not needed for our argument, but using this we deduce that f of r times m is 0, which means r times m is also inside the kernel of f, which implies that kernel of f is a submodule of the domain. Okay, so this shows image and kernel, both of them are submodules. So whenever we say the word image and kernel, it should remind you of the first isomorphism theorem. We have proved the first isomorphism theorem. You've seen it for groups. We have proved it for rings. And we've seen the importance of the first isomorphism theorem in those settings. Now we want to prove the same result for modules. But even before stating the first isomorphism theorem for modules, I need to define quotient of modules. So if you remember, for first isomorphism theorem, we want to show that domain modeled by the kernel is isomorphic to the image. So I need to say what it means to mod out a module by another one. I need to define quotient of modules. So in the next proposition, we are going to define quotient of modules. So suppose M is a module and N is a submodule. So here, similar to the abelian groups, there is no extra condition on the modules. I don't need to assume, you see, for groups, we need this normal condition. For rings, we need this ideal condition. For modules, I can simply take a submodule. So N is a submodule of M. Then I can mod out M by N and put an R module structure on this. This is similar to vector spaces. If you remember, for vector spaces, we showed that if W is a subspace of V, then we can define the quotient V modeled by W as a vector space. This has a similarity with the modular structure, and the same argument indeed works for an arbitrary ring R rather than a field. Okay, but let's repeat the argument. So suppose M is an R module and N is a submodule. Then we want to define a scalar multiplication on the quotient of M over N. What is quotient? Notice that M and N are abelian groups. So that means I can definitely look at M over N at least as an abelian group. Now, the next level that I want to go is to define a scalar multiplication on this abelian group M over N. So what is the scalar multiplication? I pick a scalar R and I pick an element inside the quotient. Let's say it's represented by the element M. I simply multiply R by M and consider this coset that R times M represents. Of course, it's not clear a priori why it is well defined. You can ask, what happens if I choose different representatives? If n prime plus n is the same as n plus n, do I end up getting the same cosets? Of course, I'm not going to get the same coset representatives, not necessarily, but the cosets are going to be the same. That's what I need to show. So that's the first thing. We are going to show that it's a well-defined function. As soon as we show that it's a well-defined function, because we are doing a scalar multiplication and addition with respect to the coset representatives, it is rather easy to see that with respect to this multiplication, M over N, it turns out to be an R module. And we call it the quotient of M over N, or simply M mod N. Moreover, from this definition, we can see that the map that sends the quotient map in the abelian setting, which sends an element of M to the coset that's represented by that element is not only an abelian group homomorphism, it is also an R module homomorphism. And again, from the group theory part, we already know that P sub n, this natural quotient map, is a surjective map, and its kernel is nothing but the module that we have modeled by. Okay, so these are the statements that we want to show, that again, this scalar multiplication is well defined. Then we define the natural quotient map, P sub n. We discussed that the image of this surjective kernel is n. Okay, so let's see why this is the case. Let's start with why it is well defined. Suppose that I give you two cosets, two coset representatives that give you the same cosets. That means that the difference between the coset representatives belong to this subgroup, submodule n. I want to show that R times M1 is the same as R times M2 mod n. That means I need to show that R times M1 minus R times M2 is inside n. Okay, how can I do that? I know that M1 minus M2 is inside n, and n is a submodule. That implies that R times, that means that n is closed under multiplication, from which we can deduce that R times M1 minus M2 is inside n. Again, because n is a submodule. From here, we can deduce that, okay, we use distribution law, we deduce this. So here again, I need to point out one quick thing. So here, if you notice that I'm writing down, so let me write it over here, R times minus m, I'm replacing it by minus R times m. What does that mean? This means that I'm claiming that when I add this guy to R times m, I get 0. Let's see why this is the case. This plus R times m. Why is this guy 0? So of course I can factor out R. Negative m plus m is 0. And R times 0 is 0. So that's why I can actually pull out this negative and write down R times negative m as negative R times m. So this is used over here, where instead of writing R times m1 minus plus R times negative m2, I wrote R times m1 minus R times m2. And that's an element inside this submodule. That means these are the same cosets. These represent the same cosets. So R times m1 plus n is the same as R times m2 plus n. And that's exactly what we wanted to show. This shows that this scalar multiplication that we are defining is indeed a well-defined operation on R cross m over n. Now one can easily show that m over n is a module. Let's quickly check one of the distributions. So let's say I want to see why R times summation of two cosets is like R times the first coset plus R times the next coset. So this is distribution on the module side. But what does this addition mean? This addition means that I have to add the coset representatives and then look at the coset. What does this scalar multiplication mean? It means that I have to multiply R by some scalar by some coset representative and then look at the coset. And then now I can use the property of M being an R module and use distribution on the module side and write this R times M1 plus R times M2 and then look at the coset. Similarly, I can do the same for these terms. I end up getting that this is the same as R times M1 plus R times M2 plus n. You see, the key point is, as soon as we show these are well-defined operations, all the computations are done at the level of coset representatives. And therefore, we get all the properties of M, because all these operations are essentially inside M with an extra decoration plus n. We already get that. So from here, we get that we have distribution both on the module side and the real side. We get that 1 times m is the same as m, and therefore the cosets are going to be the same. So altogether, we get that m over m is indeed an R module. Now, the rest of the argument about the quotient maps are automatic, but let me quickly recall what the statements were. From the group theory, we already know that the natural quotient map is indeed a surjective map. And the kernel of this is the normal subgroup, or the abelian subgroup here, that we are modding out by. So the kernel of the natural quotient map is nothing but n. The only thing that remains to show is why this is an R module homomorphism. So that means we already know that this is an abelian group homomorphism, so it only remains to show that it preserves scalar multiplication. So let's apply P sub n to R times n. What does that mean? This means I have to look at the coset that R times m represents mod n. This is how we define the scalar multiplication, that this is nothing but R times the coset that's represented by m, which is R times the natural quotient map applied to m. So that implies that P sub n is an R module homomorphism. Okay, so now we are ready to go to the first isomorphism theorem. Okay, what is the first isomorphism theorem? Let's start with the statement. The statement says that f is an R module homomorphism from m to m prime. So it's an R module homomorphism, similar to the group theory and ring theory. We want to show that f bar from m mod out by the kernel of f to image of f, where f bar of a coset that's represented by m is sent to the value of f at m, is a well-defined R module isomorphism. So again, f bar of a coset that's represented by m is sent to the value of f at m. A priori, it might be unclear why it is well-defined, but we have already discussed it in groups, and therefore, from the group theory side, we can deduce that f bar is a group isomorphism because of the first isomorphism theorem for groups. And notice that f is an R module homomorphism, and therefore it is a group homomorphism. So using the first isomorphism theorem for groups, we deduce that this f bar is a well-defined group isomorphism. So the only thing that's remained is to show that f bar is an R module isomorphism. Again, we already know that it's a group isomorphism. We already know that it's a bijection. We already know it's a group homomorphism. So the only thing that's remained is to show that it preserves scalar multiplication. So let's pick a coset that's represented by m and some scalar r. So suppose I'm giving you r, some coset representative, and I'm asking myself, what happens if I look at r times the coset that's represented by m and evaluate f bar? What is this? You have to start with asking what this scalar multiplication is. Scalar multiplication happens at the level of coset representatives. So it is r times m plus kernel of f. Now, what is f bar of this? By definition, it's nothing but f evaluated at this coset representative. So it is f of r times m. But f itself is an R module homomorphism. So f of r times m is r times f of m. Now, f of m is f bar of the coset that's represented by m. So altogether, we get that f bar does preserve scalar multiplications. It's already proved to be a bijection, and it's proved to be a group homomorphism. So altogether, we get that it is an R module isomorphism. So the first isomorphism theorem gives us a concrete isomorphism between the quotient of m by the kernel of f and image of f. Now, let's go back to the case of vector spaces. So there are many things that do not work in the case of modules, but nevertheless, we start with vector spaces and get inspired by them and then we look at modules and try to see to what extent the result that we already have for vector spaces hold in the more general setting of modules. Now, one of the results that we have proved on vector spaces is the following. That if I start with a vector space that is spanned by finitely many vectors, alternatively, I can say a vector space that is finitely generated, then we prove that such a vector space has a finite basis. And having a finite basis implies that such a vector space is isomorphic to f to the n. So again, altogether, on the vector space side, we have proved that a vector space that is finitely generated, that means it is spanned by only finitely many vectors, is isomorphic to f to the n for some integer n. Okay, so this is a result that we have proved for vector spaces by showing existence of basis for a vector space. Now, to what extent do we have this result? Can we prove this result for an arbitrary module? Can I impose certain condition for the rings to deduce this type of result? But before I get to prove this, I need to say what it means for a module to be finitely generated. Okay, so let's start with a module M. And let's suppose that N1 and N2 are two submodules of M. So I'm going not only to define what finitely generated modules are, but I'm going to also give you some extra operations between submodules of M. So suppose N1 and N2 are two submodules, and M1, M2, Mn are elements of the module capital N. Then intersection of these submodules is again a submodule. We can also add two submodules and end up getting a new submodule. But what does addition mean? Addition simply means that I pick an element from the first one, I pick an element from the second one, and I add them. We have seen the same phenomena when we discussed summation of two ideals. The same applies here. I start with two submodules, and then I add every element of the first one by every element of the next one. I get a new subset of the module M. And my claim is that this is a submodule of the module capital M. Now go back to these elements that we have. We want to understand the smallest submodule that contains these elements. Remember, if m sub i's are inside the module M, every scalar multiplication of m sub i's are inside the module capital M. And because M, capital M, is an abelian group, every combination of them, every summation of them would be also inside this M. So altogether, we get that we need to consider linear combinations, but this time R linear combinations of m sub i's in order to guarantee that all the needed elements in a subspace that contains m sub i's are already there. So in fact, we show that the set that contains all R linear combinations of m sub i's form a submodule, and it is the smallest submodule of M, which contains m sub i's. We denote this either as before as angle mi's and close angle. We call it the module generated by m sub i's, or we write R m sub n plus R m sub 2 and so on. And of course, this notation suggests that I am multiplying m sub 1 by some scalar and then adding it to scalar multiples of other m sub j's. So that is my claim. So these are the things that I want to show. So in this lemma, we are discussing intersection of submodules being a submodule. summation of two submodules being a submodule, and how elements of the module generated by finitely many elements look like. Okay, let's start with part A and part B kind of at the same time. I want to say that the intersection and summation, not union, summation, union is actually never a submodule unless one of them is a subset of the other one. It's a good exercise. I leave it to you to show that if N1 union N2 is a submodule, then either N1 is a subset of N2 or the other way around. Okay, so union is out of picture, but summation is always a submodule. Okay, so let's see how we can show this. On the group theory side, we have already proved that intersection and summation of two subgroups is always a subgroup. In fact, for an arbitrary group, if the group is not abelian, we still can define product of the groups, subgroups. The product of subgroups is not going to be necessarily a subgroup, but when it is abelian, it is going to be the case. In fact, if one of them is a normal subgroup, then the product would be a subgroup as well. In any case, we are in the abelian setting, so we don't need to discuss that anymore. From group theory, we know that intersection and summation of two subgroups are still subgroups. Okay, now we want to show that these sets are closed under scalar multiplication. So I pick an element from these sets, I pick a scalar R, and I need to multiply and show that it is still inside this set. So let's pick some element M inside the intersection of N1 and N2. Let's pick some scalar R, and let's multiply them. Notice that M is inside N sub I. N sub I is a submodule. That implies that R times M is also inside N sub I. N sub I is closed under scalar multiplication. R times M is inside M1 and N2, so it is inside the intersection. That shows the intersection is an R module, or submodule. Now let's go to N1 plus N2. So let's pick some element inside N1 plus N2. That means M is of the form N1 plus N2, where small n1 and small n2 are elements of capital N1 and capital N2. I multiply M by R, and I need to show that it is still inside N1 plus N2. So I pick a random arbitrary scalar, and I multiply R by the summation. But notice, when I multiply R by summation, I can use distribution on the module side and get it like this. Now notice that R times N1 is inside capital N1 because capital N1 is a submodule, small n1 is an element, and being a submodule is closed under scalar multiplication, so we get this. Similarly, R times N2 is inside N sub 2. So this means that I'm writing R times M as summation of one element inside N1 and another element inside N2, which means that this R times M is inside N1 plus N2. Okay, so good. So this shows that N1 plus N2 and N1 intersected N2, both of them are submodules. Now I want to go to the submodule generated by M sub i's. I need a bit of caffeine. Okay, so let's see. First, I start by arguing that every submodule of M that contains the elements M1, M2, Mn should contain all the R linear combinations of M sub i's. And therefore, our candidate set is a subset of every submodule of M that contains M sub i's. So if capital N is a submodule and it contains m sub i's, then we want to say that this N contains every R linear combination of m sub i's. So because N is a because N is submodule, we already know that it is closed under scalar multiplication. So for every index I, Ri times m sub I is inside this N. Now N is also a subgroup. That means it is closed under addition. So I can add these elements of N, which means I can add R1 times M1 plus R2 times M2 and end up getting an element inside N as well. That means the set we were interested in, meaning all the R linear combination of m sub i's, is indeed a subset of this module. Okay, so in order to show this is the smallest submodule that contains m sub i's, I need to show two other things. First, why is this guy a submodule? Second, why does this guy contain m sub i's? So if I show these two coupled with this inclusion, I'm done with the proof. Because knowing that this is a submodule, knowing that this set contains m sub i's and it's a submodule, shows that it is among the submodules that contains m sub i's. But then coupled with this inclusion implies that this is the smallest one. There is nothing that can be smaller than this. In fact, everything that contains m sub i's should contain this. Okay, so let's see why it is a submodule. I pick two elements. I look at the difference, show that the difference is still an R linear combination of m sub i's. And I multiply it by some element inside R and say that it is still an R linear combination of m sub i's, from which we can deduce that this set is a submodule. So let's pick two elements, x and x prime. So x is an R linear combination of m sub i's with coefficients small r sub i's, and x prime is another R linear combination of m sub i's by coefficients r sub I primes. And I look at the difference, x minus x prime. Notice that by the thing that we are, so by reordering the terms, it's an abelian group. By reordering the term, I can put the ith terms close to each other. This means that r sub I times m sub I minus r sub I prime times m sub I prime. Remember, with this type of argument, we showed that negative r times m is negative r times m. So instead of writing this, I can write it as r sub I. So here we have the other side. So in this part, we showed it for the other side. So here I argued why r times negative m is negative r times m. So there we are showing why negative r times m is the same as negative of r times m. It is important over here because we have negative r prime times m, but instead of this I'm going to write down plus minus r sub I prime times m sub I. So this way I can factor out m sub I and get to this equation. And as you can see, oops, what happened? And as you can see over here, where am I? Okay, so it's over here. So as you can see over here, this is still an r sub I linear and r linear combination of m sub i's. It is still in the same set. So this means that this is a subgroup because it is closed under taking difference. Now, in order to show that it's a submodule, it's enough to argue why it is closed under scalar multiplication. I pick a scalar and multiply it by x, and then I use the fact that I can distribute on the module side and write it as r times each one of the factors. Next, I use the fact that the multiplication, scalar multiplication, is compatible with multiplication inside the ring and end up getting another R linear combination of M sub i's. So altogether, we deduce that this candidate set is indeed a submodule. It is a submodule that contains all the submodules that is contained in all the submodules that contain M sub i's. So too many inclusions. So the last thing that I need to argue is why this submodule contains M sub i's themselves. So this means I need to write down M sub i's as an R linear combination. So I need to write down M sub 1 as an R linear combination of M sub i's, M sub 2 as an R linear combination of M sub i's, and so on. But there is a simple candidate for our R linear combination. We just impose coefficient 1 for the ith term and 0 for the other terms. We know that 0 times everything inside the module ends up being 0, so this part is just 0, adding zeros, so I get 0. The same is true for these terms, so the only non-zero term would be the ith term, and by our assumption of modular structure, 1 times anything is 1 times m is always m, so 1 times m sub I is m sub I, which means m sub I is an R linear combination of m1, m2, m sub m, and therefore m sub i's do belong to this candidate module that we have, and we are done. This module does contain m sub I, and every other module that contains m sub I should contain this module. So it's the smallest submodule that contains m sub I. We say a module M is finitely generated if it is generated by a finite subset m1 mn. Or alternatively, I can say we say a module is finitely generated if there are m1 mn such that every element of M is an R linear combination of M sub i's. Similar to groups, let's also define cyclic R modules. A module M is called a cyclic R module if it is generated only by one element. So if M is generated by one element, it's the same, and by this argument that we have here, it's the same as saying that every element is some scalar times M. If this is the case, we call M, the module capital M, a cyclic R module. Now the next lemma is both a good exercise for the first isomorphism theorem of R modules, and also a pretty nice statement that gives us a fairly good picture of cyclic R modules. So suppose M is an R module, then it is a cyclic module precisely when it is isomorphic to a quotient of the ring R as an R module. Notice that here, this quotient, I'm thinking about it as an R module and not as a ring. So you can also think about it as a ring, but this isomorphism makes sense only at the level of modular structure. So this isomorphism is true as R modules. So M is isomorphic to the quotient of R by I at R modules, where I is some ideal. So that's the claim, that M is a cyclic R module if and only if it is a quotient of R by some ideal of R. Let's go, it's an if and only if statement. I have to show that why the left-hand side, why being cyclic implies that it is isomorphic to R over I. Next, I'm going to show that why R over I is a cyclic R module. So let's start with why, if M is a cyclic module, then it is isomorphic to R over I. So the general trick is that whenever I give you a module generated by M sub 1 M sub n, then I have a natural map from R to the n to M, a surjective map from R to the n to M. So let's see what I'm talking about in this special case of cyclic modules. Because M is generated by this small m, every element of this module is the scalar multiple of this generator small m. So I pick this as my function. So for every scalar that you give me, I look at multiplication of this scalar by m. So I get a function from the set of scalars R to my module R module m, capital M. Because this module is cyclic, because it's generated by this element m, we get that it is surjective. Now, my claim is that it is not only surjective, but also an R module homomorphism. So an R module homomorphism, I forgot to write down. Let me write it down. Homomorphism. So it's a surjective R module homomorphism. Again, as I've already mentioned, because the module generated by M consists of elements that are scalar multiples of M, we can already deduce that F is surjective. Now, I need to show that F preserves addition and multiplication. So let's pick two elements inside the ring and ask ourselves, what is F of R1 plus R2? By definition, it is this scalar times M. I do have distribution law, so I can write it as R1 times M plus R2 times M. This one is F of R1, and this term is F of R2. So I end up showing that F preserves addition. Now let's see why it preserves multiplication. So let's pick an arbitrary scalar and some arbitrary element of the domain. So, and ask ourselves whether or not R times F of R prime is the same as F of R times R prime. What is F of R prime? F of R prime is nothing but R prime times M. So I need to multiply R by this. We know that the scalar multiplication is compatible with a ring multiplication. So R times R prime M is the same as RR prime times M. And that means I'm multiplying RR prime by M, which is F of RR prime. So altogether, we end up showing this claim that F is a surjective R module homomorphism. Therefore, by the first isomorphism theorem of modules, we deduce that M as an R module is isomorphic to R mod out by the kernel of F. But remember, R submodules of the ring R are precisely ideals of the ring R. So kernel of F being an R submodule implies that it is an ideal of this ring. So kernel of F is some ideal I, and this isomorphism gives us the desired isomorphism. M is isomorphic to a quotient of R by some ideal. Okay, very good. So this implies that left-hand side implies right-hand side. Let's go the other way around. I want to show that the right-hand side implies the left-hand side, which means I need to show that R over I is cyclic as an R module. Every element of R over I is a coset. It's R plus I, where small r is an element of the ring capital R. But this R plus I is nothing but the scalar R multiplied by the coset that's represented by 1. So that means as an R module, this module is generated by 1 plus I, the coset that's represented by 1. So the coset that's represented by 1 generates this R over I. In particular, it's a cyclic R module. So this completes proof of this lemma. So we have a fairly good understanding of cyclic submodules. Now, one of the things that they've mentioned earlier was that for vector spaces, and that's how I motivated on studying finitely generated modules or even defining them. So one of the things that we mentioned about vector spaces was this statement that if a vector space is finitely generated, then it's isomorphic to F to the N. And then we went to the study of finitely generated modules, and then cyclic modules was a special case of that. Now, next we are going to mention that this phenomena actually do not hold true if I work with a ring that is not a field. So let's see what I'm talking about. So suppose I give you a ring and it's not a field. Not being a field implies that it has an element that is not a unit. So I'm assuming that it's a unital commutative ring. So an element is not a unit if and only if the ideal generated by that element is a proper ideal. It's a proper non-trivial ideal, assuming that A is not 0. So as soon as I know that R is not a field, I can find some ideal that is proper, non-trivial, and ideal. Now I can look at R over I. That's a cyclic R module. In particular, it's a finitely generated module. But my claim is that it is not isomorphic to R to the n for any integer n. So why is that the case? What is special about this guy? The point was that I is a non-trivial proper ideal. Because it's proper, R over I is not 0, and therefore n cannot be 0. It cannot be nothing. So that's first observation. Because this is proper, this is not 0, n is at least 1. Now, next I want to argue that this isomorphism cannot happen. Why is that the case? What do I know about I? I is not 0, so it does have some element that is not 0. Now, every other element that you give me, or every element that you give me inside this quotient, it can be represented by this element. When I multiply it by R naught, I get the coset that's represented by R naught times R. But remember, R naught is inside this ideal. This ideal is closed under multiplication. So R naught plus R is inside this ideal, which means this is the coset. This is the trivial coset. Which means R naught times every element of R over I is 0. So we found a non-zero element of the ring, and that can kill the entire module R over I. So we say that it annihilates the module. So R over I has annihilator. In fact, the ideal I annihilates R over I. So no matter what element I pick from the ring, from the ideal I, it's going to annihilate the module R over I. Okay, so we have this statement, but next, if we do have an isomorphism, if assuming the contrary, we have an isomorphism from R over I to R to the n, when I apply f to R over I get a surjective map to R to the n, and R naught times no matter what I throw at it is going to be f of R naught times that element, and that thing is 0, which means that R naught is going to annihilate image of f. But f is an isomorphism, so R naught is going to annihilate image of f, which is R to the n. In particular, R naught times the vector 1, 1, 1, 1, 1, 1 is the 0 vector, because it annihilates the entire image, and the entire image contains 1, 1, 1, 1, 1. From there, we can deduce that R naught times this is 0. But that's not possible, because when I multiply R naught by this vector, I get R naught, R naught, R naught, R naught, and that's supposed to be 0, which means that R naught is supposed to be 0, but that's not the case. We chose it in a way that it's not 0. You get the contradiction, and that's exactly what we wanted to get. So very good. So we showed, this shows an example where I'm giving you a finitely generated module which is not isomorphic to R to the n for some integer n. Now, this means that there is no hope of having this kind of general basis type of result or isomorphism type of result. If you think about it, the main issue is linear independence. So here we have these elements that I can multiply by R naught and end up being 0, but neither the element nor R naught are 0. So we have this issue of linear independence. Now let's avoid that for now and focus on finitely generatedness. So suppose, again, going back to vector spaces, suppose that I start with something that's finitely generated. So we said that we cannot show it is necessarily f to the n, but can we argue that it's going to, so you see in the case of vector spaces, we could talk about dimension, and we showed that if I start with a finitely generated vector space, then every subspace is going to be finitely generated. In fact, the minimum number needed is going to be at most the minimum number needed for the entire space. That was the dimension. Can we have the same result for modules? Is it true that if I start with a finitely generated module, then every submodule of this module is again finitely generated? Okay, so that is the question. Let's recall again over here. So the question is, so again, for vector spaces, we showed that if V is a finitely generated vector space, then every subspace of V is finitely generated. Now, to what extent can we have a similar result for modules? One of the simplest modules that we have discussed, the simplest R module that we have discussed, is R itself. So we said that R can be viewed as an R module, and of course it's a cyclic module. It's generated by 1. In fact, every quotient of R is cyclic. In particular, R modeled by the zero ideal, or R itself, is a cyclic module. It's finitely generated. It's generated by 1 element. But on the other hand, we've discussed that submodules of R are nothing but ideals. Now, saying that a submodule of R is finitely generated as an R module is equivalent to saying that, do I have finitely many elements such that every other element of this ideal is an R linear combination of these elements? But that means that, is that ideal finitely generated? So if I repeat the top question in the language of ideals, what I'm asking is the following. Is it true that every ideal of R is finitely generated? So again, is it true that every ideal of a ring R is finitely generated? If you think about it, we have reached to this type of question when we were discussing uniqueness of factorization into irreducible elements for PIDs. And so there we had to exclude existence of certain strictly ascending chain of ideals, and we showed that that phenomena happens if and only if every ideal of R is finitely generated. In fact, that was our motivation to define Noetherian rings. So if you remember this, if you don't go and look it up in the lecture notes, we have proved this proposition that every ideal of the ring R in this lecture will be is always a unital commutative ring. So every ideal of R is finitely generated if and only if R is Noetherian. So that was, what was Noetherian? We called a ring to be Noetherian if it has no infinite ascending chain of ideals, strictly ascending, no infinite strictly ascending chain of ideals. What does that mean? This means that if I give you an ascending chain of ideals, then from some point on, they should be the same things. So then I sub n naught should be the same as I sub n naught plus 1 and so on for some integer n sub 0. Okay, so this was the definition of Noetherian rings. And we have shown this important proposition that a ring is Noetherian precisely when every ideal of M is finitely generated. So this means that this result gives us at least another interpretation of when all the ideals of R are finitely generated. Now, this brings us to the definition of Neutherian modules. An R module M is called Noetherian if a similar ascending chain condition holds. What does that mean? So if it does not have an infinite ascending, strictly ascending chain of ideals, infinite strictly ascending chain of submodules, not ideals, submodules. What does that mean? This means that if I give you a chain, an ascending chain of submodules, if M sub i's are submodules of M, and this is ascending, then from some point on, they are supposed to be the same field, the same modules. So if this is the case, then we call the module Noetherian. So notice that because submodules of a ring R, as R submodules, are precisely ideals, then from this definition, it is clear that R is a Noetherian ring precisely when it's a Noetherian R module. So being Noetherian as an R module, you see R is the same subject, the same object, but at one hand, we are putting the hat of being a ring and view it as a ring. And on the other hand, I'm thinking about it as an R module. So for both of these type of objects, we have the concept of being Noetherian. For a ring, being Noetherian means that every chain of ideals should, every ascending chain of ideals should stop at some point. For Noetherian, for modules, being Noetherian means that every chain of submodules should stop. But the key point is that submodules of a ring are precisely ideals of that ring. So being a Noetherian ring is equivalent to saying that it's a Noetherian R module. These are equivalent phenomena. Now, we have the following similar statement for modules. An R module M is Noetherian precisely when every submodule of M is finitely generated. So M is Noetherian precisely when every submodule of M is Noetherian. The proof is kind of identical to the case of rings. Let's quickly go over this. This is an if and only if statement. So we start with the assumption that M is Noetherian. I want to show that every ideal is finitely generated. Every submodule is finitely generated. Suppose, to the contrary, that there is some submodule N which is not finitely generated. Using this contrary assumption, I'm going to create a strictly ascending chain of submodules and get a contradiction. Okay, let's start with the zero ideal. Zero ideal is, of course, finitely generated, and it's a submodule of N, so it cannot be an entire N. I can find something inside N that's not inside N sub 0. So let's pick one such element, a non-zero element, indeed. Now let's look at the ideal generated by M sub 1 and call it N sub 1. Again, N sub 1 is a finitely generated module. It is in fact cyclic here. Because N is not finitely generated, N sub 1 cannot be N. So I can find something inside N that is not inside N sub 1. Add it to N sub 1 and consider the module generated by M1 and 2. This is again finitely generated. N is not finitely generated, so I can find M3. Add it to M1 and 2. Again, end up getting a finitely generated module. N is not finitely generated, so I can repeat this process, end up getting a chain, a strictly ascending chain of submodules, and that gives us a contradiction. So, so far we proved that if M is a Noetherian R module, then every submodule is finitely generated. So in the next lecture, I am going to continue with the other side, and we further study modules. So we study a bit on the abstract side, and then we go back to zeros of linear equations and ask ourselves how we can address solving these equations, at least when I'm working with a ring that we have more information about its ideals. As we have discussed, it is important to have a good idea on the structure of ideals of this ring. More precisely, we will be working with Euclidean domains, and I will mention that a similar result holds for PIDs. Okay, so till the next lecture.